In this video, we're going to look at worked example 1 from learning outcome 3 from the statics unit. This example asks us to find the magnitude and nature of the force in each of the members of the structure. So just to remind ourselves, the members are the physical parts of the structure. So here's one, here's another, and here is a third. Along the way, we can also work out what the size of the two reaction forces R1 and R2 are, but that's not our primary aim in this question, although we will work those out. As well as finding out how big they are, that's the magnitude, we want to find out the nature. So are these ties or are they struts? So are they under tension or are they under compression? Or indeed, could there be a redundant member within the structure? It's unlikely in a simple triangle, but we'll work it out. So how we'll go about finding this out is using Bose notation, or what we call nodal analysis, which means taking each node, and for example, this is a node here, it's a point where members and forces intersect, and doing a scale diagram to show that to work out the forces based on our understanding that every node will be under static equilibrium. That is, all forces that meet at any node will balance out to give us zero net force. The only other thing we need to know to begin is that to do nodal analysis, we can have a maximum of 2 unknown forces. We need to know at least one, and we can have as many as 2 unknown forces. So you can see that the 2 bottom nodes are not going to be good candidates to start because we don't know any of the forces here, and we also have 3 unknowns. However, starting up at this node at the top, we can see we have 3 nodes coming together here. So 3 forces coming together, 2 members and 1 external force at this node, and we know the size of the external force. So this allows us to make a beginning on this node. So we can do our nodal analysis here. So we're going to start off looking at the node at the top of our diagram here. Now, as I said, this is going to be a scale diagram, which means that we have to represent our forces on a scale on paper. And I think a sensible way to do this is to use a scale like this. And let's say that our scale will be 1 centimeter is equal to 1 kilonewton. So that means the very first line I'm going to draw is the 10 kilonewton force acting down the way, which will be 10 centimeters long. So this is the first thing that we ever draw. And to try and keep our different forces distinct from each other, I'll use different colors to represent them on the diagram. So let's use red for this first node here. And I'll quickly sketch in, just so you can see what I'm doing, I'll just sketch in just now which node we're looking at. So looking at the node that has 10 kilonewtons coming down, and we've got 2 members here. We don't know anything about these. We know the areas, we label the spaces between forces with capital letters. This is D, this is C, and this is B. Just taking that from the diagram. And we can also label all of our lines as well as we draw them. We'll do that one step at a time. So this is a little sketch. It's definitely not to scale. It's definitely not accurate for angles. We'll work on that in a second. So let's first of all draw in a line of 10 centimeters pointing down the way, which represents our external force. I think that's reasonably good for the whiteboard. So that's 10 centimeters with the ruler. Draw to arrowhead at the end, direction. Well, direction in a vector diagram is always important, but it's incredibly important in these questions. We will not solve without it. I should have also made a little cross at the start there, just to indicate our starting point. So I'll do that there. This is our starting point. And a little cross to begin with. So we have a 10 kilonewton force heading down the way, and we can label this force as well. This is between spaces C and D. So this is vector, little c to little d. That's what we call it, CD. And this is what's going to help us find the other two forces, because the other vectors are going to be also labelled from this. So where we've got CD, we're going to have DB, and we're going to have BC as well. So let's consider these other two vectors in turn. I'm just going to move our scale slightly because I think it might end up getting in the way. So I'll just shift it up here. What do we know about the vector BC? If I can colour these in as I go, so let's do that. Got a red vector coming down. So our vector BC is this vector here. It's going to be sloping up at an angle. It needs to pass through this point. It needs to pass through this point C. So either B is somewhere up here or it's somewhere down there. We know this because it has to be in that direction. All the forces within our members are inside the member, and so we've got a starting point for how do we find this. But we actually know exactly what angle this is running at. This line BC, it doesn't come from nowhere. On our diagram, it comes all the way from down here, and we see it's a 30-degree angle it's coming up at. So this line that I'm going to draw in, I'll just sketch it in just now, this should have a 30-degree angle here. So we actually have something quite precise to draw. So I'm going to draw that in just now. We're sketch. And if we line our ruler up at the top, I'll do a little dotted line across the top of this just to give us somewhere to measure the angle from. So it's a bit neater than an actual cross. We can always draw a wee dotted guideline that's going to help us. I need to measure around 30 degrees, and of course, on a real paper and pencil example, you do this with a protractor. So I can draw a line here. This is 30 degrees to the horizontal, just like that angle down that I've circled at the bottom left. That's how I know it's 30. And I know that B is either somewhere up here or it's somewhere down here. I can just draw a line off in both directions, which is why it's quite good to do these in pencil when you're doing them, so you can make things all rub out any bits you don't need. So I've got this line BC. So B is somewhere along the blue line. I don't know if it's up to the left or down to the right yet. So I'll draw that in. So that's a line BC. So I've got CD, BC, and I'm going to have line DB as well. And DB, I'm going to call this in green here. Again, I'm going to have a force that runs along the length of this member, so it has to be pointing either up the way or down the way, but in that direction, so if it's one or the other. And I know it must pass through the point D, so this point at the other end of the beam, it's going to have the external force going to have to come through here, because it has to be DB, so either B's down here or B's up here. But maybe we can think, well, hang on, we thought B was here or here, so probably B is in this region over here. That's certainly going to be. So let's take away these sketches and draw this in accurately. And again, we actually have a specific angle to draw in here. We've got this angle of 45 degrees, which means that's the way that this force is pointing up from the horizontal. So again, I'm going to take my ruler and draw a little dashed line, make a measurement of to make my measurement of the angle from the dashed line here. And I know this line DB is going to run upwards an angle of 45 degrees from the horizontal. So I can draw my line in like this. I'll line this up with the end of our external vector. And I don't even need to, I can draw the illustration, I can draw down to left, but I know it must be coming up to the right, because the only place where the blue and the green lines cross is up here. So this point where these two cross, this is the point B. I can write that in. So I'll tidy up this a little bit. I'll just rub out this excess line here. I don't need any of this because we don't have a vector running up there. We don't have a vector running down here either. And beyond the point where they meet, that is also the end of that. Now, as to what direction these are going in, well, remember in statics, we always have to come back to what we start with. So we've started up here, that's our starting point, and we have to end there as well. And we've come down the way like this. Our red arrow's pointing down the way, which means our green arrow must be followed to come down to the bottom. The only way we can go is up, so green's pointing up this way, and then blue must be pointing back to the start. So we've got the direction of the forces. So we've sketched this in our little diagram on the left. It means that the blue one is pointing towards the node, and the green one's also pointing towards the node. And that tells us something useful. It tells us whether these are ties or struts. And we've got to think carefully about this. What we have found is the internal force, and the internal force reacts to whatever's happening to our beam. So if our internal forces are acting out the way, it means they're acting against compression. So that these two beams have to be under compression because internal forces are acting out the way. So what we have are two struts here. And what you'll find is useful, and we use this in examples a lot, we can write down the names of all of our members and the forces inside them, and also the nature of them as well. So we'll start with the table here. We have a table for a member and the force. We're going to get these in a second, they're in kilonewtons, and we're also going to get their nature as well. And the first two, well, we've got a few different ones we're going to be dealing with. Let's look at the first two we found in. We have got the one that we have called BC. Let's put you in here. And then we've got the one we called DB. And the way around the letters are in the table doesn't matter because they act in both directions. I've just labelled them. Calling that BD in the table wouldn't be wrong. The order just matters in the diagram where we're working around our shape in order to find the balance. So we know these two are, we know they must both be struts because these are under compression, and that's why the internal forces are acting up the way. And over in our main diagram here, we can show that we're going to have forces acting towards the nodes here. But remember, these act at both ends. So down at this node, that force will be acting down the way there because it's acting outwards on both sides. And the same for CB, it'll be acting out the way here as well. So we know something about the direction of the forces heading towards the other nodes. We also need to get the size of the forces. Now, because this is a scale diagram, we can actually measure it. So what we're going to do, as we've done in learning outcome 2, we're going to measure the length of the line here, and we can use that to convert it back into kilonewtons. So count along here, 2, 4, 6, 8, and I get about 8.5, 8.9, I think, maybe, sorry. 1, 2, 3, 4, 5, 6, 7, 8, and then just short of 9. So I get about 8.9 for mine. That's 8.9 centimeters. 1 centimeter is equal to 1 kilonewton. So I'm going to get a force of 8.9 kilonewtons here. And we can do the same thing for the force BC. I'll measure that as well. And that looks just more than 7 1/4, so that's 7.3. Maybe my line's slightly off, but DB should actually be 8.8 from the course notes. So since mine's close enough, I'll call it 8.8. Now again, as with learning outcome 2, if we do make a little error with this, or even if we do our best, but our answer is slightly different than the answer in the solutions, there's nothing to worry about because there's a little bit of room for discretion with that. So we've done our first node, and it's important that when we're faced with a question like this, we do put a real effort into getting the first bit right. Usually in an assessment question, we'll get 2 or 3 nodes to do. In this question, there's a total of 3. So not getting too bogged down and worrying about what comes next. Get the first bit right and we can take it from there. But we've got these three and we've got them in place here. We can also label them with the sizes as well, just so that we know. So this is 10 kilonewtons. This one here was 8.8 kilonewtons. And this one here in blue is 7.3 kilonewtons. Now we come to look at the node the bottom left here, this node here. So we have one force that we know and two forces that we don't. The force that we know is this one here, the 8.8 kilonewton force. But what we've got to be careful with is that while this was pointing up the way at the first node we looked at, which makes sense, we go back and look at this member, it's pointing up the way up here, it points down the way towards this node. So when we come to doing our second node, we want to remove the arrows off the members that we're using the next time around. So we can remove these arrows here, but they've done our job for us in terms of the direction here. So we can, I'm not going to zoom in to tidy that up a bit more, but this time looking at our second node, we have this line here pointing down the way like this. And then we're going to have two other forces in play, but not the red or the blue ones, because they are exclusively up here for this bit. We don't need to deal with this here or this here, because they are up at that node. We've got two other forces to deal with. We'll sketch in what's happening. So that we'll call this node 1. The first one, that was node 1. Node 2, let's write this in here. Node 2. Well, we have this force we covered green previously, that's acting down the way. So we know it always acts out from both ends of the beam if it's acting out the way. And we worked out the size of that was 8.8 kilonewtons. So we found that out. We know we've got a reaction force acting up the way. We'll make this one purple. And this is the force R1. And then we've got a force that's could be acting to the left or it could be acting to the right, but it's a further force, and we'll mark this one in orange, that's acting this way. And you notice I've not put an arrowhead on it because we know the green force acts down the way because it's a strut. Struts act towards the node wherever they meet them. And we know the purple force is acting up the way because it shows us in the diagram that reaction force is acting up the way. What we don't know, and what's important to know, is which way the orange line is going. It's going to be going left or right, but we don't know. Again, we can label the spaces. This is space D over here. This is space B here. And this is space A. And so we're going to have the vector BD, because it's heading down from B to D. So we've got the vector BD. We've got the vector DA. And we've got the vector AB. So these are all the things that we need to consider. So let's draw in AB first of all. Now, sometimes, I'll quickly do this and put it back in. Sometimes when we're first allowed to do both notation, it'd be good just to forget any of this exists. And then just work with this vector. I'm not going to do that because I want to learn to do Bose notation with the full diagram. But ignoring the rest of it, you can see we've got a vector and we're drawing another one in. But I'll leave this stuff in just now. What you need to remember is we don't need these things in this diagram. I've color coded to show it's only going to be the purple vector and the orange vector that we have to concern ourselves with. So we've got DB or BD acting down the way. We got that from the previous part of the question. We now need to draw in the orange vector AB. So we know it has to join up with this point B, and we know it's a horizontal line. So we can draw a horizontal line off in either direction. And I'll just sketch it across the So it's going left, it's going right. That's us saying that point A is either over here somewhere, or over here, or somewhere along this line. But it's to the left of B, it's to the right of B. And then I've got the line DA to sketch in as well. Now, DA is a line that must pass through, and I'll go back to my purple pen for this. It must pass through point D, and it's also definitely acting up the way. So it's not up or down, it's definitely acting up the way because it's a reactive force. The diagram's told us that that force R1 acts up the way. So actually what we can do here is we can take our ruler, get it to be vertical, and line it up. And you'll see it's going to overlap our red lines from before. It doesn't matter, we already have the information we needed from that. And draw a line coming up from point D to where the orange line is. And I can stop there. Take my ruler away, now I can rub out any extra parts. Okay, we didn't need any of this stuff over to the right because the orange line runs to the left, and we can rub out this stuff here as well. And so what's happening with our lines? Well, we know that the green line is acting down the way like this. We know the purple line is acting up the way like that because it's the only way it can go. And so we can then fill in from here that this orange line must be running to the right because we have to have that loop. So this was our start this time. I should rub out the other start just so that we can see what we're doing in this one. If this was our start this time, we come down the green line, up the purple line, and back along the orange one to where we got to. And this gives us the information we need to finish off our table. We can see that the orange line is going to be acting away from the node here, it's acting to the right, which means that on our structure at the node, we have a force acting in the way and a force acting in the way. And remember, internal forces act in the way to combat tension. They're trying to stop the bar being pulled apart. So internal forces are acting to overcome that. So that should be point A. So our force, our member AB, AB here, must be a tie because the internal forces are acting in the way away from the nodes. So we can say that it must be a tie. And we can get the size of AB by measuring it as well. Again, it's a scale diagram. So if we measure this, we're going to get a value in centimeters we can convert to kilonewtons. So if I line this up, it's going to be 246 and a bit, and it's 6.2, which is in fact the correct answer. So we can set 6.2 kilonewtons because it was 6.2 centimeters. And we can also find the sizes of R1 and R2. We don't always need to do that if we're not asked to, but we can here, so let's do it. R1 is the purple line, so we can measure that off the diagram as well. So lining that up, 2, 4, 6 and a bit. And this turns out to be 6.4 centimeters, and so it's 6.4 kilonewtons. And we don't have a nature because this is not an internal force, it's an external force. So we do not applicable or do a wee dash. And then lastly, we can find R2. Now there's two ways to find R2. We could recognize that we have another node here. We know two of the forces. We have this blue force for the first part that's coming down the way, and we've got an orange force that's coming this way, and we could have, well, let's make up another color we've not used yet. We have a yellow force coming up the way, and that could be R2. We could draw a diagram, or more simply in this case, we can remember the other rules still apply. Going back to our structure, the downward forces have to equal the upward forces. We have one 10 kilonewton force down. If R1 is 6.4 kilonewtons, R2 must be 10 minus 6.4 is equal to 3.6 kilonewtons. The two, R1 and R2, still add up to give us 10 kilonewtons. So we can save ourselves doing a third analysis of the node. And that's how we do it. The tricky part in these questions is definitely when we have to draw a second or even a third node over the top of the first diagram. But hopefully you can see by reusing our diagram, it saves us having to draw in that line again. And so we save ourselves quite a lot of work on our scale diagram. But that's how to do example 1.